Dear students, after completion of all the 4 modules, now we are entering into the 5th module. In this module, I am going to discuss about the laser and optical fibers. So it may take 3 to 4 lectures to complete this portion, including the problems. And in this first lecture, I will discuss the 3 types of interactions of radiations with matter, and also an important derivation, that is the expression for energy density in a radiation, especially the laser radiation emitted by a source. Let's understand the basic principles involved in producing the laser. These basic principles are also known as the different ways in which the radiation interacts with the matter. Here I have shown 2 energy levels. One energy level is known as the ground state. The other one here is the excited state. The ground state means it is the lowest energy state of an electron or an atom or a molecule or an ion. So when a system is given or when a material is given, that may be consisting of the ions or the molecules or the atoms, but basically all are comprising of electrons. That's why sometimes while talking about the excitation and deexcitation process, I use the term that the electrons are excited. If I say that the electrons are excited, you can simultaneously understand that the atoms are also excited, molecules are also excited, or the whole material itself is excited. So excitation means basically it is the enhancement of energy. If you supply a certain amount of energy to an electron when it is in the ground state, that is in the 0 point energy state, which you understood while discussing the application of Schrodinger's equation in module 1 to calculate the energy eigenvalues. We had used Schrodinger's equations where I had told you that the system can never have 0 energy, but it can have the lowest energy at a given instant of time in the absence of external energy sources. That is known as 0 point energy or the ground state energy. That is actually represented with E1 here. If you supply a certain amount of energy equal to h nu, you just recall that h nu is the energy of a photon or the quantum of the radiation. So that amount of energy, if it is provided to electron or the atom, the energy of that electron or the atom will be increased. Assume that the energy of electron is 1 electron volt in the ground state. Now if you supply 0.5 electron volt to that electron, its total energy becomes 1.5 electron. That 1.5 electron is represented with this energy level E2. So difference is 1.5 minus 1 electron volt. That is the energy of the photon or the quantum that has been supplied to the electron in the ground state. So when the energy is given to a system, it gets excited. We say that the total energy is increased. And the excitation and de-excitation of electrons or atoms or ions or molecules in a material depend on the energy which we supply to the material. There are 3 types of interactions of radiation with matter when the matter means material is exposed to a radiation. The first type of interaction is the induced absorption, which I have already mentioned, although I could not mention the term induced absorption. The process is explained, means induced absorption is the phenomenon in which the atoms of the ground state absorb the supplied energy and increase their energy value to a higher value, that is equal to E2. That is known as excitation process. That is also called induced absorption. And the second type of interaction of radiation with the matter is known as spontaneous emission. The other one is the stimulated emission. Let us understand one by one. I have already mentioned about the induced absorption, that when you supply a photon or the energy to the atom of the ground state, that will absorb this photon and goes to higher energy level, and it will settle down in this energy state. Means not physically, it is getting the energy E2, means it is raising its value of energy to the value equal to E2, and that energy of a particular atom or electron will be with that electron or atom for some time. That time is of the order of 10 power minus 8 second only. The time that is about 10 power minus 8 second is natural in almost all materials. It is the natural tendency of every material or the particles of that material. Particles means they may be electrons or atoms or molecules. It is natural tendency for them to have the life of the order of maximum of 10 power minus 8 second after absorbing energy. That means they can hold the supplied energy or absorbed energy for a maximum of 10 power minus 8 second in the material. And after 10 power minus 8 second or within that time, they will come back to the ground state. That is about the transition, downward transition process. Okay, so induced absorption is clear now. It is an excitation process in which when you supply certain amount of energy to the atoms of the ground state, they absorb and increase their value to higher value, that is E2. And now let us look into the second type of interaction of radiation with the matter. Spontaneous emission of radiation. Spontaneous emission of radiation takes place only if the atoms are already in the excited state. That means in order to have the spontaneous emission, basically we have to supply, initially we have to supply the energy to the system, either in the form of optical energy, that is light, or in the form of electrical energy, or in the form of heat. But heat cannot be used for producing the laser due to some reasons which I explain later. But electrical energy and optical energy are widely used because they are advantageous in producing the laser. Right. So, spontaneous emission of radiation is the phenomenon in which the electron or the atom that comes back to the ground state will release the amount of energy that it absorbed earlier during the excitation. That is known as the spontaneously emitted radiation. Spontaneous transition or spontaneous deexcitation means this is the atom, this is already in the excited state, means higher energy state. If this atom loses that energy on its own, then it is known as spontaneous transition or deexcitation. The loss of energy by an atom or by an electron is known as the deexcitation process. So during the deexcitation process, the energy is lost by the atoms or the electrons. That is diagrammatically shown this way. If this atom before the deexcitation it is here, and after the deexcitation it can be shown like this. So it is coming down to this. Coming down is not physically, but its value is said to be coming down. Of course, within the atom, electron will come from higher orbit to the lower orbit. But the physical meaning is that energy of the electron is reduced, or energy of atom is reduced, or energy of the system of atoms or the material itself is reduced. That is the deexcitation process. If this deexcitation takes place without the support of any external sources, then it is known as spontaneous emission. For example, when a person speaks on himself or herself without any question asked by someone, then it is known as the spontaneous speech. And after your question, if somebody speaks, it is the stimulated speech. So here, similar to that, spontaneous emission means the radiation is emitted without the support of the external sources of energy. The transition of electrons takes place from higher energy level to lower energy level on their own. They won't need any kind of support by the external agencies. This is the spontaneous emission. The main demerit of this kind of transitions or emission of radiation is that the emitted radiation is incoherent. Means different photons will have different wavelengths. They can move in different directions. That's why the emitted radiation is non-unidirectional and even non-monochromatic. Because of the different wavelengths, obviously they are non-monochromatic. So that spontaneous transitions are not helpful in producing the laser. Only stimulated emission is helpful. That we understand now. You can observe an equation that I have written here. Delta E is equal to H nu is equal to E2 minus C1. That is actually the amount of energy released by the electron or atom during its de-excitation. Earlier, while discussing the induced absorption, I was saying that H nu is the amount of energy absorbed by the atom or electron. So you think in the line of law of conservation of energy. If you supply a certain amount of energy to the system, that system will give the same amount of energy or less than that. If some other types of losses are there, you will get radiation of the same energy or less than that. It is not possible to get higher energy value. And here in this case, this equation represents that the energy released by an atom is equal to the difference between the energy levels. So that I have already described in the previous slide. And stimulated emission. In this case, again the excited atoms are required in the material. So initially we supply the energy and make the atoms to excite to higher energy level. After the excitation, these atoms may come back to the ground state on their own. That is the spontaneous de-excitation. But there are some special situations wherein these atoms can stay for a long time in the excited state. That means they can hold the energy for a long time. And that energy that is with the atoms can be lost by these atoms during the excitation if that de-excitation takes place with the support of the external sources of energy. I am showing here that there is a photon, incident photon, which is going beside the excited atom. And this incident photon can interact with the excited atom. During the interaction, you can say that it is the collision of incident a photon with the excited atom. During this collision, this atom can come down to the ground state by losing a photon. Which photon? That photon was absorbed by the same atom during the induced absorption phenomena. That photon will be lost by this atom after this photon interacts with it. This atom is already in the excited state, so it may not absorb the energy that we supply. If it does not absorb, then during the collision, this atom loses the energy. If it is not absorbing the photon, naturally this photon does not lose its energy. So that during the emission of radiation by the de-exciting atom, this incident photon simply accompanies the photon released by the atom. So that virtually we say that two photons are produced when one photon stimulates the excited atom. So that the photon is stimulating the excited atom. It is interacting with the excited atom. It is colliding with the excited atom. During that interaction, this atom loses the energy. That energy appears in the form of a photon. Here, there are two photons produced virtually because one photon is the same incident photon that is accompanying with the photon emitted by the de-exciting atom. So that we say that two photons are produced during the interaction of one photon in the excited atom. So this is the stimulation process. During the stimulation process, if the atom de-excites, it is known as stimulated de-excitation, and the radiation emitted during this process is known as stimulated emission of radiation. And the advantage of this particular type of transition is that the emitted radiation is coherent, means the emitted photons have the same wavelength, they will have the same phase difference, means constant phase difference, and they move in the same direction, hence they are called unidirectional. Monochromatic because they have the same wavelength, coherent because they have the constant phase difference and the same wavelength. The photons which are emitted in this process may interact with other excited atoms also. For example, this photon interacts with this atom, producing these two photons, and these two photons may interact with two other excited atoms, producing four more photons, because each photon virtually produces two photons, and those four photons emitted may interact with four other excited atoms, producing 8 photons. This is how the energy is amplified. There is avalanche multiplication of photons which increases the intensity of radiation. This is how light is amplified, and this is therefore useful in producing the laser. And now I am coming across very important part of this particular topic, especially in view of examination. I am going to derive the expression for energy density of laser in terms of Einstein's coefficient. Here I am repeating the three phenomena which I described so far: the induced absorption, spontaneous emission of radiation, and the stimulated emission of radiation. They are repeated but in terms of mathematical terms. So far I did not use any mathematics. Now I am going to see the mathematical angle of view for the same three phenomena. So induced absorption is already known phenomenon. In this case, we supply the energy to atom of the ground state, which will absorb the energy of the incident photon and goes to higher energy level. And if there are a number of atoms in the ground state, let us say n1 number of atoms exist in the ground state in unit volume. Number of atoms per unit volume n1 is known as the number density or density of the atoms or the electrons or the ions. And these number of atoms may absorb the supplied energy and go to higher energy level. Just for representation sake, I have taken only one atom or one electron, but there may be n number of atoms, so that when you supply energy in the form of optical energy or in the form of the electrical energy, they absorb energy and go to higher energy level. The number of absorptions, means number of atoms absorbing the energy per second per unit volume, is called rate of absorption. That rate of absorption depends on the energy density which we supply. E nu is the energy per unit volume of the radiation that is incident upon the material in order to excite the atoms. So E nu is the energy density. N1 is the number of atoms per unit volume in the ground state. That is the population of atoms in the ground state or density of atoms in the ground state. So rate of absorption depends on these two quantities. And to replace this proportionality symbol, a proportionality constant is used, B12, that is known as Einstein coefficient of induced absorption. It is the probability, its physical meaning is that it is the probability of absorption per second per unit volume. Because although there are hundreds of atoms or electrons in the ground state, every electron, every atom need not excite. Some may not absorb energy, so that there is the matter of probability. So probability of absorption per second per unit volume is represented in terms of B12. And spontaneous deexcitation, it is again the phenomenon of deexcitation of atoms or electrons on their own without the support of external agencies or external sources. And this spontaneous de-excitation is purely independent of the energy density of the incident radiation, because as I already mentioned, spontaneous de-excitation does not depend on external sources, but the number of atoms available in the excited state is important. On that number of atoms per unit volume, the rate of spontaneous transitions depend. Means number of atoms undergoing spontaneous de-excitation per second per unit volume. R21 SP represents the rate of spontaneous transitions. Means it is the number of atoms de-exciting per second per unit volume by their own. And this is depending only on the number of atoms in the excited state. N2 is the number of atoms in the excited state in unit volume. And proportionality symbol used here is A21, which is the other Einstein's coefficient representing the probability of spontaneous de-excitations per second per unit volume. And the next one is stimulated de-excitation. So stimulated de-excitation takes place with the support of the incident photons. That's why the number of atoms undergoing stimulated de-excitations in a second per unit volume, that is known as rate of stimulated transitions, depend on energy density of the incident radiation as well as the number of atoms in the excited state. Proportionality symbol used here is B21, which is known as Einstein coefficient of stimulated transitions. It physically measures the probability of stimulated transitions per second per unit volume. Now, the three factors have been discussed. At thermal equilibrium condition, means when the material is maintained at the constant temperature, the rate of excitations must be equal to sum of the rates of de-excitations. If there are 100 of atoms in the ground state, for example, 40 atoms may de-excite spontaneously and remaining atoms may de-excite after stimulation, so that the sum of the de-excitations must be equal to sum of the rate of excitation at thermal equilibrium condition. Now you have the expressions for R12, R21SP and R21ST. Here 21 means rate of spontaneous transition from energy level E2 to E1. That's the meaning. R12 means rate of induced absorption such that the excitation from E1 to E2. That's the meaning of this equation. And I am substituting the expressions for R12, which we derived previously, B12 E nu N1, and R21SP was derived, and it is here R21ST. So they are substituted. E nu is in two terms. Take this term to left hand side so that you will get this expression. Take it common. Bring this term inside the parenthesis to the right hand side, so that you will get B12 N1 minus B21 N2, and bring this N2 down to the denominator so that N2 comes to the denominator of each term. So N1 by N2, N2 by N2. So this cancels and B21 remains, N1 by N2 is here. Now again take B21 outside, so that if you bring B21 outside, this becomes B12 by B21, N1 by N2 minus 1, because if I take this outside, 1 will remain, but here since we don't have B21, we have to write B12 by B21 if you take B21 common. That is shown in this equation. B21 is written outside, therefore B12 by B21 is appeared. Now you have a ratio N1 to N2, number of atoms in the ground state, number of atoms in the excited state in unit volume. So now apply a factor that is known as Boltzmann factor. Boltzmann had proposed in a theory that for a given material, ratio of the number of atoms in the ground state to the number of atoms in the excited state is always equal to exponent h nu by kT. This is the theory proposed by Boltzmann. This is what we are employing in this equation in the place of n1 by n2. And if you write it, you will get this expression e power h nu by kT. And now this equation can be compared with the Planck's law of radiation. Planck's law was discussed in the module number 1 while talking about the black body radiation. That equation was similar to the one which I have written here. But I had expressed that equation in that module in terms of the wavelength, but here I am taking in terms of the frequency because the equation which we have derived is in terms of the frequency. And you also can observe that we don't have the differential term d lambda. There the equation was E lambda d lambda is equal to 8 by hc divided by lambda power 5 into 1 by e power hc by lambda kt minus 1. That was the equation. Multiplied by d lambda was also there. And that equation or this equation, any one can be used here, of course. So, since we don't have the differential term, here we are not having the differential. If we differentiate this equation, we get the same equation by taking nu is equal to c by lambda. It is possible to obtain the same equation which we discussed in module number 1. Okay, now I am going to compare these two equations. Reason is that this is the equation applicable to all the sources have the ability to emit radiation. This is also the expression for the energy of the radiation itself. Therefore, both should be similar. In that case, this in the place of A21 by B21, we have 8 by h nu cube by c cube. Therefore, you can write that A21 by B21 is equal to 8 by h nu cube by c cube. And in the place of B12 by B21, what do we have? We have unity. Therefore, B12 by B21 is equal to 1. And therefore, this equation infers that the probability of induced absorptions should be equal to probability of stimulated deexcitations, which means that the suppression of spontaneous transition should occur in order to have the high energy density in the emitted radiation. So, this equation, this relation is important to understand. So, this relation suggests that the probability of induced absorption should be equal to probability of the stimulated deexcitations. And if we can suppress the spontaneous transitions, then it is possible to get laser of highest intensity. Now, the same equation is written in this way. This equation A21 by B21 is simply written as A by B. A21 is taken as A, B21 is taken as B. And since B12 by B21 is equal to 1, it is written this way. Okay. So, this is the expression for the energy density of the laser beam produced by a laser device. And although it is possible to have a material for producing the laser, that material has to satisfy certain conditions. Otherwise, it cannot produce the laser, because in nature, thousands of materials are available, but none of them have the ability to produce laser. That is the reason why people have used those materials, there are elements available naturally, and prepared the new materials by mixing one with the other in the proper proportion and developed the material. And such materials have the ability to produce the laser if and only if they satisfy the two conditions which I am going to describe now. One is known as the metastable state, the other one is known as the population inversion. Metastable state means it is one among the excited states which has very long life as compared to the ordinary excited state. Its life is too long. Such an energy level or such an excited energy level is known as metastable energy level. For example, in this diagram, I have written three energy levels. E1 represents the ground state, E2 and E3 are the excited states. And you need not take only two excited states. For a given electron, there are hundreds of energy levels. There is the chance for an electron to have hundreds of energy values. That's the reason why we say that an electron can have a number of allowed energy levels. When you supply certain amount of energy, that can go either to this energy level or to this energy level or to higher energy level, but it depends on the amount of energy. The metastable state, as I was mentioning, is the one that has very long life. I was mentioning in my previous part of discussion that in almost all the materials, the electrons or the atoms can be in the excited state for a very short interval of time, of the order of 10 power minus 8 second only. And if there is an energy level, excited energy level, which can hold these excited atoms for a long time of the order of 10 power minus 3 to 10 power minus 4 second, then its life is said to be about 10 power 5 times longer as compared to the life of the excited atom in the ordinary excited state. Such an energy state is known as metastable state. Here in this diagram, E2 can be assumed as the metastable state and E3 is the ordinary excited state. When we supply certain amount of energy, these atoms excite to higher energy level, either to E2 or E3 or any other energy level. And deexcitation is usually stepwise, means they usually do not directly deexcite. Instead, they deexcite first to this energy level, then to this energy level. And during the deexcitation, since this is short-lived energy level, that is 10 power minus 8 second is the life of the atoms in this energy level, they will come and settle down in this energy level. Since it is metastable state, they can stay here for a long time. And if they can stay here for a long time, the energy level is said to be metastable state. And long time means how much? It is a millisecond. For the atoms, it is very long time. For example, for a human being, life is 100 years. Let us say 100 years. We say that it is very long life. If there is a person who ends his life at the age of 20 or 25, we say that he was too young and his life was too small. So similarly here, 100 year, how we feel it as very long life, similarly the atoms or the electrons feel as if they live very long time here. So the atoms can stay here for a long time, hence this is known as the metastable state. Now let us understand population inversion. Population means it is the number of atoms in a given energy level per unit volume. And that density of atoms or population will be higher in the ground state before we supply the energy. Because almost all the atoms will be staying in the ground state, means they all have the lowest energy before the supply of energy. And if you supply the energy, they will absorb and go to higher energy levels. And if all the excited states are ordinary excited levels, then they will come back to the ground state. The process will be continued in such a way that the ground state is always more populated than the excited states, if there is only spontaneous transitions, because within 10 power minus second they return. That's why it is possible that the ground state always has higher number of atoms. But in a material, if there is a chance for the existence of a metastable state, then the excited atoms will come and stay here for a long time. So within 1 millisecond, about 10 power minus 3 to 10 power minus 4 second, most of the atoms of the ground state will excite and settle down here. Means at that instant of time we say that this is more populated than the ground state. So the number of atoms in the excited state is higher than the number of atoms in the ground state. This is known as population inversion phenomenon. So population inversion is the process of inverting the density of atoms, and population inversion is possible only if there is a metastable state. In absence of metastable state, population cannot be inverted. But what is the necessity of population inversion? Population inversion is necessary because the stimulated deexcitations can take place only if the population is inverted. As I was mentioning, population inversion helps material to undergo stimulated transitions. So stimulated transitions are possible if the population is inverted. Population inversion is possible if there is the existence of metastable state. Why stimulated emissions start only after the population is inverted? It is because the incident photons are actually stimulating the excited atoms. If there are more atoms in the ground state, then the supplied photons will be more preferred to go to the ground state and to interact with them. So that if the ground state is more populated, incident photons will be busy exciting these atoms only. They won't bother about the excited atoms. If you can make this ground state relatively vacant, then the supplied photons can interact even with the excited atoms, or they can stimulate the excited atoms and bring them down to the ground state. That is how stimulated transitions can begin. So stimulated transitions begin after the population is inverted. So a material that has the capability of producing laser will satisfy these two conditions. If a material cannot have the metastable state or the population inversion, then it is not possible for it to produce the laser, but it can produce the light. For example, tungsten can produce the light in an incandescent lamp. The LED can produce the light. The tube light can produce the light. That is, fluorescence phenomenon is involved in the tube light. Sun produces the light. Candle produces the light. They are all the spontaneous emissions of radiations. So that the two conditions have to be satisfied by the material in order to produce the laser. We will discuss the requisites of a laser system in my next lecture.